Hi, welcome to Weather and Forecasting. This is Module 2, and we're going to get started just talking about solar radiation and Earth-Sun balance and seasons, so Earth's axial tilt. One of the key things to remember when we're talking about weather and conditions is that weather is just the act of the atmosphere moving surplus energy around. So it's an energy balancing game. There's locations where there's too much energy, most specifically heat energy, in one location, and weather in the form of things like clouds and wind and other major weather events is just pushing that energy surplus to places of energy deficit. We're just following the rules of physics. And so energy, the main source of all energy on the surface of our planet, is obviously the electromagnetic radiation provided by our nearest star, our sun. There are multiple types of energy, but there's two major categories that we can put energy into, and that is kinetic, energy that is actually in motion, and energy that is in storage or not in motion at this time. And even the different forms of energy can fall into these categories. For example, when I talk about electrical energy, I am talking about energy in motion, so it is kinetic at this moment, even though it's specifically the energy of electrons jumping. When I'm talking about something like chemical energy, until I go to utilize said chemical energy, it is in storage, therefore it has potential to provide certain energy. So if I take a piece of wood, that wood has chemical energy. When I light it on fire and I start it burning, it's providing and becoming kinetic. Once again, slide showing you kinetic versus potential energy. This is kind of important. We can measure the amount of energy in an item by utilizing temperature. If a temperature is warmer, we would say that that object has more energy. So the actual molecules of that object are vibrating farther and faster than if it's colder of the same item at the same temperature. So if I take some water, not talking about freezing, so it's liquid form, and I take its temperature and it's 150 degrees, that has pretty high energy. Where if I take the temperature of the water and I find out that it's at 40 degrees, I would say that it has very low energy at this time. So the molecules of the liquid water are vibrating slower at 40 degrees than they are moving or vibrating at 150 degrees. There are three ways that I can categorize the transference of this heat energy in the molecules, and that is through conduction, convection, and radiation. Conduction is movement through a substance. We typically would say this is the action of molecules bouncing into one another. So let's take, for example, a spoon. If I take a spoon and I put a heat source on one end, it will transfer that heat molecule by molecule. So this molecule will start to vibrate and it'll bump into this molecule, and it'll do this molecule to molecule on down to the far end of the spoon till it's down here, and I can feel the heat from this heat source moving down the spoon through the molecules. This is a conduction energy activity. Convection is a transference. Now, convection takes place in fluids. Now, remember, fluids can be both our liquids and our gases. Don't forget gases. The atmosphere is gas. We did this in the last chapter set. So the gases are the fluid actions of our atmosphere. You think of the convection activity to build a cloud. I have these molecules. They have gone from their liquid or solid state on the Earth's surface. They've turned to gas form. They are warmer and therefore lighter, and they are flowing up because they have less density. So they are moving up in their order of operation. So convection. Obviously, if they cool off and sink back down, I form what's called a convection cell, where it rotates up and down, right? The last one is radiation. Radiation is the transference of heat energy, and it requires no medium. Radiation is what we think of as electromagnetic spectrum. These are photon particles. This is specifically things like sunlight, right? Sunlight is a form of electromagnetic radiation. We ourselves put out thermal infrared radiation. So we actually radiate energy off of our bodies. And that's why when you get close to a person, you don't have to actually physically touch them. You can just hover your hand and you can feel their body heat. Yes, you're feeling their radiant energy flowing off of them. Just talking about quantity and quality of radiation. So I can measure different radiations energy level, whether it's a high level radiation or a low level radiation. I can do this by taking in their wavelength. Photon particles can be measured as a particle, an individual, or they can be measured based on their wavelength. And the smaller the wavelength, the higher the energy. Think of a line of little kids jumping, right? If I take those little kids and I go boing, 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 if I set them all nice and close together and they bounce, boop, 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 really close together, we're talking about very high energy to do that activity. On the other hand, if I spread out my wavelength, I make the bounce happen here and then here and then here, it takes longer, it's slower, less energy involved in that. Talking about quantity and quality of that radiation and measuring electromagnetic waves. Intensity of wavelength, emitting of radiation. Once again, these are things where you can just read, they're kind of definition based. Black bodies are objects that are absorbing radiation. So when you hear of something being black body, it means that it's absorbing the radiation that's hitting it. This is the slide that I'm looking for. So here we go. Radiation, when we talk about electromagnetic radiation, can be divided up into different spectra. And the small wavelength stuff, the really tiny stuff, are X-rays. So we can go all the way down and talk about X-rays, very small electromagnetic radiation waves. Then we get into our ultraviolet waves, and they come in A, B, and C flavors of wavelength. And these are very short wave, high energy. Then our visible spectrum, the ones that we have developed an organ to actually observe or see this wavelength of light, right? And that's our visible spectrum. The reason why we have an organ that does this is because it's the most potent material that comes off our sun. So the most common form of this energy coming off the sun itself is in the visible spectrum. So that's what's making it to the Earth's surface. From there, when I get on the other side of my red in my visible spectrum, I get to my near infrareds. Then I get into my middle infrareds, and then finally my thermal infrareds, which are over here. So that's what you think of as like heat, actual heat energy, where you can feel it, sensory. Once again, we have a sensory to determine that, thermal infrareds. And then we get into really big stuff, which is things like TV waves. Well, microwaves are up here, TV waves. And then we get into FM radio and then finally AM radio waves. Those are all wavelengths of electromagnetic radiation. And we just built tools to utilize them, right? Characteristics of radiation, once again, definitions and terms. Take your time, read through. I'm going to move quickly because we can just look at these things in our time. So once again, the divide up, short wave radiation, small stuff, long wave radiation, long stuff. So think of everything visible spectrum down is short wave. Everything near infrared up is long wave. This is talking about planetary variation and surrounding wavelengths and solar constant. So the exact amount of energy hitting our Earth. One of the key things to remember about solar constant is that our sun is constantly doing a nuclear reaction. So it's undergoing this nuclear reaction, which is putting out material, most specifically plasma material, which releases electromagnetic radiation. This electromagnetic radiation is traveling at a specific distance towards our Earth. And while it's not directly aiming at us, it's directing its energy in a radius around it. We are in the sun's path at an exact coordinate. So we are at a specific rotation, right? That means that we will receive a similar amount of sunlight at all times. And while there will be some fluctuations in the solar constant, for the most part, it's consistent, hence the solar constant. And so we can write our book on it. How much solar radiation we will receive from the sun is something that's a known and understood development. So on that note, I'm going to pick up with part 2 of Module 2.